Before we go to analyze the compression process, we would see what are the objectives. So first one is to calculate air pressure and temperature before and after compression process. Next one is to calculate indicated power or work, and next one is to obtain compressor efficiency, and to calculate free air delivery rate, which is expressed in kilogram per second or meter cube per second. Here we have some assumptions that the working fluid is assumed as a perfect gas, one thing. And if you can assume it as a perfect gas, you can apply these equations, that is simple equation of state. Usually these assumptions are used to calculate or estimate pressure P, volume V and temperature T of the working fluid. So here we have PV is equal to MRT, and each time we have a constant mass here inside this. We compress a constant amount of fluid, so M can be considered as constant and R is also a constant here. Now this PV, if you take this to the left side, PV by T is equal to K1, and PV raised to N is equal to K2, which is the relation for P and V for a polytropic process. Here there are two cases that we consider. First one is compressor without clearance volume, that is the volume at the end will be 0 and in the beginning also it will be considered as 0. Now the compressor with clearance volume, and we will discuss about multi-stage compressors also. Now here if you consider this cycle, it is not actually a cycle because the every time fluid is changing here, so we cannot consider it as a cycle. But temperature, pressure, it will be coming back to the same value, but the fluid is changing every time. So actually you cannot consider it as a thermodynamic cycle. Still we say it as a cycle. In the previous class, I have told you to find out the area under the curve. Actually, it is not the area under curve. It is the area that is left hand side of this curve, in compression curve. Okay, so this is DABC. Now, what is this area? This is ABCD, area ABCD, and that will be 1, 2, 3, 4, 1, the same area. Now that is equal to area under 1 2, that is area under 1 2 means this is 1, this is 2, so this area, okay, V2 V1 1 2 plus area under 2 3, that is here 2 is there and 3 is there, area under, that is this bigger triangle, sorry, rectangle, and we have to minus subtract the area under 4 1, this is our 4 1. If you subtract this smaller area from this whole area, you will get this DABC. Now you have this work which is a WB, that is WB means boundary work, that you have already studied in your thermodynamics class, and that work is calculated as integral 1 to 2 PdV work. Boundary work is PdV work. And here, as it is a polytropic process, I consider PV raised to N is equal to C. What I should do, PdV means I am integrating with respect to dV, and P should be in terms of V. So P here is equal to C by V raised to N or C V raised to minus N. Now I substitute it here for this P, that is V raised to minus N dV, and I know that integral integral x raised to n is equal to x raised to n plus 1 by n plus 1. According to that equation, you have V raised to 1 minus n, and applying the limits 1 to 2, you have V2 1 minus n minus V1 1 minus n. So C is equal to PV raised to n, and PV raised to n is equal to constant means you can write it as P1 V1 raised to n is equal to P2 V2 raised to n. Now I substitute it here. Here also I can substitute P1 V1 raised to n, and here n and 1 minus n, that will get cancelled out, and here 1 by n is taken outside. Here it is said that this work must be done on the compressor. That means this system is doing work on this compressor, I just write the opposite sign of this one. So this will be n minus 1. So this is P2 V2 minus P1 V1 by n minus 1, which is the area 1 to 2. Fine. This is 1 to 2. This whole area, that is P2 V2 minus P1 V1 by n minus 1, plus this area under 2 3. So this is a rectangle, so this is length into breadth. Okay, this will be length P2 and breadth is V2. So you can write down the areas P2 V2 minus of this rectangle, that is a smaller rectangle here. This is length is V2 and breadth is P1, so P1 V1. Here you can see P2 V2 and minus P1 V1, that is common in both these terms, so I can take it outside. Here 1 by n minus 1 plus 1 will be there. So if you calculate, this will be n by n minus 1, P2 V2 minus P1 V1. Now if you apply PV is equal to MRT, if you apply this equation here, this is P2 V2 and this is P1 V1. So I can write this as MRT2 and here it is MRT1. And here you can see that MR is common here, so I will take it outside. N by n minus 1 MR here inside the bracket, that is T2 minus T1. So it can be considered as a general equation, or this can be considered as the equation for polytropic process. Now see here, we have the relations for polytropic process. P1 V1 raised to n is equal to P2 V2 raised to n, and we have the general equation P1 V1 by T1 is equal to P2 V2 by T2. Now you can see here P1 by P2 will be equal to V2 raised to n by V1 raised to n. Here also you will get the same relation, that is P1 by P2 is equal to something. If you take it here, you will get some relation. Now equate this P1 by P2 from here, as well as you can equate the expression that you got from here with each other. You will get the ratio of pressure here, and you can get the relation between those two, as well as temperature ratios and pressure ratios. By simple math you can find out the relations. Now here you can substitute. So this equation is n by n minus 1 P2 V2 minus P1 V1. You consider this equation, W is equal to n by n minus 1 MR T2 minus T1. Now if you take this T1 outside, here it will be T2 by T1 and here it will be 1. T1 I have taken outside. So what is T2 by T1? T2 by T1 is equal to P2 by P1 n minus 1 by n. So I have substituted that expression here, and you will get this expression also for the polytropic process. Now the indicated power is the work done on the air per unit mass. The mass flow per unit time m dot is often used to compute the work done per time or indicated power. So you have already discussed about what is indicated power. Fine. So this is indicated power, that is n by n minus 1 m dot, which is mass flow rate, into R T2 minus T1. So you can use this same expression to find out indicated power. Now mechanical efficiency, it is the ratio of indicated power to the shaft power. Now we have already discussed about this. Now shaft power is equal to indicated power plus friction power. So whatever power is there in the motor shaft, that is the shaft power, and whenever we convert that to the indicated power, always there will be a friction. Okay, so that is the loss here, and if you subtract shaft power, friction power from the shaft power, you will get the indicated power. Just try to understand the physics, no need to remember these equations. Motor efficiency, it is the ratio of shaft power to the input power. Input power is the electric power supplied to the electric motor. Whatever electric power you supply to the electric motor, you won't get it as a shaft power, because inside the motor also there is some losses. So that is the motor efficiency. Now see what is the expression for constant isothermal process. When we consider it as isothermal process, PV is equal to C, that means N is equal to 1. When you consider it as a polytropic process or internally reversible process, then you can just change this value of n and you can find out the expression here also. Okay, so here if you consider n as gamma, then the process will be adiabatic process. Now for isothermal process, you can see here PV is equal to C. Now if you integrate the PdV expression, so integral 1 to 2 PdV, now I should write this P in terms of V. Now P is equal to C by V. Now I know integral dx by x, that is log x. In the same way, this is log V and we have two limits. Now applying the limits, you will get C ln V2 by V1, and what is C? That is PV. It can be P1 V1 is equal to P2 V2. I can write this C as P1 V1 or P2 V2. Okay, so you will get the same expression here. Now from here P1 V1 is equal to P2 V2, you can write what is V2 by V1. Okay, V2 by V1 will be equal to P1 by P2, and you will get the another expression. No need to by heart, just find out from the expression only. So you can remember this PV is equal to C. So from that only you can derive all these things, as well as you can write these expressions. Now if I consider this ideal gas equation, PV is equal to mRT, which is equal to C, because T is also constant here. Now this can be written as P1 V1 is equal to mRT. Okay, so this is mRT V2 by V1 or mRT ln P1 by P2. Here this is mRT only, so there is some mistake here. By this expression we can find out the area under this curve. What we need the area to the left of this curve. We can do it now. The area hatched by these black lines is given by this expression. W is equal to P1 V1 ln V2 by V1. Now we have P1 V1 is equal to constant, which implies P1 V1 is equal to P2 V2. So this area, the hatched by these red lines, this one is actually what? This area plus this area, okay, minus of this one, this area. So what is that? P1 V1 ln V2 by V1, that is area under curve 2 1, and this rectangle is P2 V2 and this rectangle is P1 V1. Actually P1 V1 is equal to P2 V2, right? P1 V1 is equal to P2 V2. So this will get cancelled out, and ultimately P1 V1 ln V2 by V1 will be our expression for work done. This is the same because adding this area is equivalent to adding this area, because these two areas are the same.